Okay, welcome to another KISSsoft module. We're going to talk about worms today. In fact, we're going to talk about worms with enveloping worm wheels specifically. And we're going to just do a follow along on this tutorial right down here in the examples. It would be this example 1, which follows this PDF tutorial 16 for worm gears. And the task today is going to be to calculate a worm gear pair with a center distance and a load rating, speed and torque. And so what we're going to do is first we're going to look at the inputs that we have, okay? And what we're going to do is we know that we're given that the effective tip clearance is 0.8 millimeters and the root radius coefficient is 0.2. And we also know that this is specified as an accuracy grade 6 DIN, and the worm's flank form is going to be a ZI flank form, or Z1 or ZI. So we are going to go ahead and look at this set of gears. We know what the inside radius diameter is going to be, and we also know the root diameter. All right, so now we're going to go ahead and start populating. The axial transverse module in this particular case is 4, that's given. The center distance is 100 millimeters, that is given. The worm has 2 starts on it, or 2 gear teeth, and the gear has 41 gear teeth. We know the worm is 60 millimeters long. We need to size this lead angle, and once we have the transverse module, the center distance, and these 2 gear numbers in here, we can actually size this at a center distance of 100 and calculate it. Go ahead, it calculates this lead angle reference for you. We accept. Now we can size this face width. It says 64.9 and 29.4. We're going to take and make this 60. That was a given, and we're going to just go ahead and populate that at 31. The material and lubrication, I'm going to change this to a 5115 case carburized steel. I'm not going to do anything with the oil at this point, and I'm going to go ahead and leave this gear as a CUSN, a copper tin 12 bronze, and I'm not going to change that at this time. We could. You can see there's some other options here, but I'm just going to leave it right there. The other information I need to populate in here is I need to change and define what the flank of the tooth is going to be for the worm gear. In this case, it's going to be a ZI. Additionally, the inner diameter of the gear itself will be 134.4 millimeters. That is a given. That's the inside radius diameter is 134.4. That's in the example text. It's the inner diameter of the gear, the large gear. And we say OK. Well, we don't have a rating. We can turn that off right now just in the meantime so we can see what we get calculated here. We get a consistent calculation, and it tells us that this is our reference operating diameter. Okay. The next thing we want to do is define a profile. Now we've been told in the information that the tooth thickness, the tip clearance is 0.8 and the root radius coefficient is 0.2. So the root diameter is 26.4. Okay. And that also is given. And the external diameter of the worm gear is 44. So that also is given. So this reference profile is not what we're going to use for the worm. We're going to change this to own input, and we can look and say, well, the root radius here, we've given this coefficient was 0.2. We're going to size this addendum coefficient, and that addendum coefficient should be 0.2 when it's all said and done. And let's do the addendum first, because that's 44 and that's a given. So if it's 44, okay, we calculate that, and we're given the addendum here, which is 26.4, and we calculate that. We get 1.2, 2, and 1. This is our reference profile. Okay, it's a DIN profile, And we're going to do the same thing for the gear, but for this I'm just going to go ahead and go find that profile because one exists. It's a DIN profile, and it's right here. 1, 2, and 1. Okay? And I can do that back here too for the worm. I'm going to just go find this DIN profile. 1, 2, and 1. And now I have a defined profile for this worm gear pair. We were told that the effective tip clearance is 0.8. I want you also to know that you can define what that tip clearance is by looking at the addendum coefficient 1 and subtract the difference between the addendum coefficient and the addendum coefficient, which in this case is 0.2. It's a factor. If you multiply that factor by the module, you get 0.8. And that's what your theoretical tip clearance should be. You're going to wonder where some of those numbers came from. That's where it came from. Okay? Tolerances. We're not going to go according to Neiman. We're going to put our own tolerances in here. And we're going to do that for both the worm wheel and the gear. The tolerances are given. For the worm, it's minus 0.1. Okay? And for the gear itself, that number, let's see here, is going to be, well, it's minus 0.04, and okay, I had the wrong number there. 0.4. This one is going to be minus 1280 and minus 1680. They're telling us that we're going to make these changes also in the example. The tip diameter is -1. That's where that -1 was. And the other tip diameter is also -1, and that's given in the first information. But they also give you a root allowance diameter, which is it's 0 to -1100, and 0, let's see, -3600 to -4730. Now, if you have your own set and you're going through, you can always define what this input is, or you can go by a standard. We know that the center distance standard is going to stay this measurement JS7. We're not changing that, so this is our plus/minus center distance value. We go ahead and solve. We have a consistent design. One last thing we have to do in our data tab is we need to define some of this information about a worm the worm wheel, which is enveloping. You can see an enveloping worm wheel is a little different than a straight worm. We have a throat radius and a throat number, outside diameter, etc. So nice thing with KISSsoft is we can size the radius, we can size the throat distance. We're going to leave this face chamfer angle at 0, but if you were interested in giving that a chamfer angle, it'd be right here. Okay, so 0 I think is a good number here. We're going to size that chamfering distance, and we're going to size the external diameter of that particular worm wheel. All right. We solve, we have a consistent number. Now we want to look at the rating for the pair, so we turn the rating on right here, and some information that is giving to us later is we have a power input of 5.3 kilowatts. The worm is driving, and a speed of 1500 RPM. We know that they want 25,000 hours of service life, and the application factor is 1.00. Okay, it automatically populates our torque based on our power and speed, which is nice. The other thing is we need to change this over to a DIN 2012. That's a calculation method. We need to look into details here, and we need to look at our pair data. So why do we need to enter this 00? Because the calculation is based on this type of a setup. So you have two bearings supporting the worm, and then you have an offset distance on there. So we can size it, and it would give you 120 over 60. However, in our case, we want 150 over 75. We hit OK. And now we're not going to consider the load spectra. We've defined our data, our profiles, and our tolerances, and we can calculate. It tells me the minimal safety is not reached. So let's look at that. So I have a minimal flank safety, it looks like, that doesn't reach. And I have a safety against wear and a safety against safety factor for the temperature is pretty good, but wear and flank safety are below the safety factors I need. Also, our total efficiency is kind of low, but our safety against deflection for that worm gear and shaft is pretty good. All right. This is why I mentioned earlier that we don't always know what our oil needs to be. If you have an oil that you use traditionally in production, you use that, of course. In my case, I don't specifically have an oil that I like or dislike, but I do know that I can try and size this, and it's going to say I need a nominal viscosity of 323 millimeters squared per second, and I'm pretty sure that the oil that I have at 40 degrees is not that. If I go in here and I open this up, I can kind of look and critique the oils I have, and if you look at this, it says 220 for that oil, and that's not going to be good enough for us. So maybe we can bump it up to the 680 and do a calculation. It still says it's not reached, but it's better. You can see that my safety factor for temperature is up and my flank safety is up. So let's go all out and find out what I need to have for an oil. I'm going to go ahead and sort this from the top down, and it appears to me that my viscosity, kinematic viscosity at 100 degrees C at 35 is not enough. So I need to bump this up, and I'm going to go ahead and bump it up to maybe this one right here. This oil, it's a little heavier. You can see the density is a little bit more. I have a higher viscosity, and let's take a look. Okay, my safety against wear was improved. My flank safety is above 1, and my safety factor of temperature is also above 1. You can also look and see that my efficiencies dramatically increased. It went from like 70 to 85, or 77 to 85, and 89%. So this is a pretty nice improvement for where we were. If I look in my specific module-specific settings and go to my required safeties, you can see I have the heating that's 1.1. Safety against deflection is 1. Against wear is 1.1, 1, and 1.1. So you could argue that maybe I'm not quite high enough on the safety against temperature. If that was the case at this point, I would maybe look at even a better oil, and maybe I look at maybe this one right here. We do a calculation. So this is negative. Let's go ahead and make that change back. I must have grabbed the wrong one. Let's look at that again. All right, 167. Oh yeah, it went down. So we could really go for a good one and get this Ultra right here, this Kluber Fluid CF Ultra. See what that does for us. Oh, not reached. So maybe that one I grabbed was the right one, right? You can click through there and choose different oils and choose your own oils as well. In my case, I happen to think this heavier oil was a better choice for me, which was right here. And we can go ahead and solve that. And I'm not getting warnings. This is pretty close to what I wanted. I would say I'm probably okay at this point. I have good efficiencies, and my rating is good. I can run a report quick, and I can look at the information that I inputted in my results. Incidentally, I want to look at that 0.8 tip clearance. It's going to be at the end of section 1. Right here, theoretical is 0.8. Okay? And that's a worm with enveloping weir calculation. Pretty simple, actually, and very quick and powerful. If you were going to make changes, you can definitely come in here and make changes to this shape of the flank. You can change this. You can save the DXF files and actually import them into the crust axis module if you have a specific shape of flank you're going to use with the design. And then you can use that shape to populate your next teeth. So this is worms with an enveloping worm gear. It's kind of a basic entry type of tutorial, but it's very powerful if you're using this kind of a gear pair combination in your designs and applications. If you have any further questions, you can contact me at Ty Warner. See ty.warner@KISSsoft.com. KISSsoft's got 3 S's in there, and I can answer your questions. And if you have other requests for information, I can deliver that information to you as well. Our homepage is www.KISSsoft.com. You can go on there and look at web demos, tutorials, and information about our products. This is a good product, worms with enveloping worm wheels. I'm Ty Warner with KISSsoft USA. Thanks for watching.